I know teachers that hate this so much that they've taken personal days rather than teach it. You know who you are, Mr. Kelly. Okay then, so imagine we've got sodium and chlorine. And if I take a sodium atom, oh, don't forget its electron, and a chlorine atom, and bring them together, I've made sodium chloride solid. That's not particularly exciting. Now let's break it up a little bit. Let me imagine taking an atom, not forgetting its electron, and taking it from the solid sodium and making it gaseous sodium. So I've atomized it. And now take that gaseous atom and rip off the electron. So that's the first ionization energy, isn't it? Now from here, I'm looking at the chlorine. Imagine I've ripped a chlorine atom off of a molecule to make chlorine gas. Again, I've atomized the chlorine. And now that atomic chlorine, I'm going to add that electron from the sodium. Whee! And it's stuck on there. And now from the sodium ion and the chloride ion, I'm going to take those and make sodium chloride solid. So there's a long-winded way to do this, and that is called the Born-Haber cycle. Let's look at two examples. So for the first example, we will try ye merry old sodium chloride. The IB loves this one. So looking at that equation, it's making 1 mole of the product from the elements in their standard state. Sodium's a solid, chlorine's diatomic and a gas. That is called the heat of formation, delta HF. So that's the heat of formation for sodium chloride. Well, that seems easy, but there's a big space all the way above. So we're going to go around the really complicated way to break that process up into its component parts. First of all, the difference is that the sodium has turned from a solid to gas. So some people like to call that the heat of gasification, but not really. Vaporization? No, not really. It's atomization. That's the better one. So it's delta H atomization for sodium, making 1 mole of atoms from the element in their standard state. Next up, notice the sodium now has a +1 charge. And so that's, and there's an electron as well. If you forget that electron, you'll lose a point. They love to take a point off for that. And by they, I mean me. So that's the first ionization energy of sodium, isn't it? Making 1 mole of gaseous monopositive ions from a mole of the gaseous atom. And finally, on this going up, increasing energy, plus, all the way up, the chlorine has gone from diatomic to atomic. So I've made a mole of chlorine atoms. Again, that's called atomization of chlorine, to make 1 mole of atoms from the element in their standard state. So that's delta H. Oh, I forgot that delta H there. There we go. Delta H atomization of chlorine. So I'm going to write the word chlorine because it's unclear to me if it's Cl2 or Cl or half Cl2. That's fine, we'll just put chlorine. Now the next one almost always goes down. If you're adding 1 electron, you're making a bond, chlorine atoms and an electron. That one's a negative, so it's going to go down on this Born-Haber cycle. If you're adding 1 electron, you're making bonds, releasing energy. So what's it called where you add an electron to an atom? It's got to be gaseous. That's electron affinity, isn't it? So it's delta H, the first electron affinity for chlorine. EA Games challenge everything. No, not that interesting. And our little sodium chloride, let's move him along. So we've gone all the way around the really complicated way to come back again to make 1 mole of sodium chloride, solid. That final arrow I put in is making 1 mole of the ionic compound from its gaseous ions. That's called the lattice energy, or lattice. If I ever have a daughter, I think that's what I'm going to call her, Lattice Thornley. Now the IB doesn't mind which way this arrow goes. If it's going down, it's negative, and if you want to make it go up, it's positive. The definition's slightly changed, of course, breaking up 1 mole of the ionic compound into its gaseous ions for the reverse definition. Either way's okay. So adding up the arrows in a clockwise manner, as you go round, you add, and when the arrows reverse, like that green one there is going the other way, they have to go on the other side of the equation. So clockwise equals anti-clockwise. So all of those equals that final one in a circle. So clockwise equals anti-clockwise. If you don't like that, the other way of doing it is that plus that plus that plus that plus that long one minus that one that's going the other way, all equals 0. So the clockwise are plus, the anti-clockwise are minus, and it all equals 0. Let's try it again, but using numbers this time. We'll choose sodium oxide. So there you can see I'm making 1 mole of sodium oxide from its elements in their standard state. Yep, sodium's a solid, oxygen's diatomic and a gas. So that's delta HF for sodium oxide. And I looked that up on the interweb net, and that's minus 414 kilojoules per mole. There's no room to put the units. Next up, I need to atomize the sodium. Now, I'm not making 1 mole of sodium atoms as a gas from the elements in their standard state. I'm making 2 moles, so I better double. I've got to double the number there because I'm making 2 moles and not 1 mole. So that's 2 times, and that number isn't in the data booklet. You have to be given it or look it up online if you're doing it external to the exam. Next up, well, I'm going to rip an electron off of the sodiums. Don't forget to retain those electrons with the plus 2 electrons or you'll lose a point. That isn't the first ionization energy of sodium. That's twice the first ionization energy of sodium because I'm making 2 moles of sodium ions, gaseous, from the gaseous atoms. Next up, I need to atomize the oxygen. So I've got half of an O2 that I need, so I've got to make O. This is where the IB likes to play a little sneaky trick, but if you know it, then you won't fall for it. They could just give you the atomization value, or they could tell you to look it up in the data booklet. So let's take a time out. If you go to the bond energies, you can see the oxygen-oxygen double bond is 498 kilojoules per mole. That's the average bond energy. So it's 498. No. That's to break a mole of bonds. But when you break a mole of bonds, you make 2 atoms. I only want 1 atom, so I'm going to have to divide by 2, my 498. Let's just delete that. Oh no, I've deleted. Oh, this is for. Oh, thank God for Control Z. All right then. Now, normally the next step is negative. The electron affinity, which is coming up next. Oh, hold on. Bond energy of O2 divided by 2. That's it. We just said that. So the next step, normally it goes down. But I looked it up in the data booklet, and this one goes up. Just be aware that normally it goes down. Now, is that the first electron affinity and the second electron affinity of oxygen? Yep, and those are also in the data booklet. So I worked those out, it's 657. Now I can go all the way down. That long arrow is the lattice, or, well, actually the lattice energy. I can't get lattice out of my head. It's making 1 mole of the ionic crystal from the gaseous ions. And that's the unknown. So let's try and work out this value. Clockwise, add them up, equals the anti-clockwise. That's one way you can do it. The clockwise values equal the anti-clockwise values. The other way you could do it is add, then minus the ones going the other way equals 0. So clockwise minus anti-clockwise equals 0. Either way, when you work that out, it comes out at minus 2526 kilojoules per mole. Oh, capital J. This is the theoretical value. Obviously, it's theoretical. You've used lots of data booklets and looked stuff up. That's the theory value. The experimental value, if you did the actual experiment. And the next assessment statement will explain what it means to have a theory and experimental data compared.